Hey everybody, welcome to chemistry, and my name is Steve Presnell, and I'll be teaching this class, which is the second part of first semester chemistry. It's called Chemistry 1B or Chemistry 110, and what I want to do now is just kind of briefly go over some of the material that we'll be covering in this class and put it into context of what we've already covered and what you may cover in the future. So the last semester you took, Chem 109, what we did is we covered chapters 1 through 6 in the book. And so now what we're going to first start off with is we're not going to start off immediately with chapter 7. We'll start off instead with chapter 8, which is the quantum theory of the atom, which describes where electrons can be found in atoms. The next thing we'll go into is periodic properties of atoms and details about ionic bonding. And then chapter 10 is on covalent bonding. We'll cover that next. Chapter 11 is next with the shapes of molecules, and we'll talk about some advanced bonding theories. And then finally, we'll go back to chapter 7 and we'll talk about the gas laws. If you decide to continue on with chemistry, you can take another full semester of it. It'll be Chem 110, and there what you'll do is you'll continue on with chemistry and you'll be learning about subjects like comparisons of liquids, solids, and gases, and then going on to kinetics and more detail about thermodynamics, and then things like possibly radioactivity. And so those are going to be covered in chapters 12 and 19 in your book. Okay, so to start off with, I want to talk a little bit about a bit of a description of the quantum model of the atom. So let me take a few moments to talk about what this is on the light board. So what the quantum model of the atom is, it's using something called quantum mechanics to understand the behavior, the location, and energy of electrons that are found in atoms. So I just used the word or phrase quantum mechanics, so let me break that down a little bit. So we have mechanics, and so what is mechanics? So mechanics is actually a branch of physics that studies the motion of objects. So it studies motion of objects. Now, mechanics in physics can be subdivided into two general categories. And so one category is called classical mechanics, and then the other category, which we study with atoms, put an L there for classical, is quantum mechanics. Okay, so there's actually a pretty important dividing line between the two, which I need to explain. So classical mechanics applies to objects that are of everyday size or much larger than that, and then they can be to some degree smaller than that. So let me talk about some of the objects that classical mechanics applies to. So one thing that you can use classical mechanics to describe is the motion of planets. And so planets are extremely large, right? They're certainly larger than a meter. They're going to be larger than kilometers or megameters or gigameters. And so we're talking about sizes that are going to be greater than terameters. And so you could use the laws of classical mechanics to describe the motion of very large objects beyond terameters. Now, also, you use the laws of classical mechanics to describe the motion of everyday objects like baseballs, for example. And so baseballs are in the meter range. And so you can continue to use the laws of classical mechanics to describe smaller objects, things like single-celled animals like protozoa, like paramecium. So you have paramecia, and so the size of a paramecium is about a micrometer, which is 1 × 10⁻⁶ meters. So again, you can use classical mechanics to describe the motion of these objects. So what are these laws, these classical mechanical laws? Well, these were developed long ago by a guy named Isaac Newton, who in 1665, largely by himself, thought of these physical laws that you can use to describe the motions of these objects. So let me give you a few of these laws. So one physical law, which you already learned about, is that the work on an object is equal to the force applied on the object times the distance that you push the object. And so that is a classical mechanical law which you can apply to all these things which I kind of mentioned here. Another maybe more important law which more describes the motion of these kinds of objects is the relationship between force, mass, and acceleration of an object. And so what that is the acceleration on an object is equal to force applied on an object divided by the mass of the object. And so that is something called Newton's second law. It's usually seen more like this: force is equal to mass times acceleration. So these laws and other laws are physical laws that you can use to predict the motion of these objects. So let me talk a little bit about what kinds of things that you can predict with these laws. So for example, let's say we're looking at the orbit of a planet around the sun. So let's say you have the sun here, and let's say you have a planet here. And so what you probably know is that the planet follows an orbit around the sun. And so this orbit can be called a trajectory. And so what is amazing about these laws is if we have some basic information about, say, the mass of the planet, how far away it is, maybe its starting velocity, what these physical laws will tell you is where that planet is exactly located on this orbit for every time that passes. So these physical laws are said to be deterministic in that they tell you exactly the trajectory that an object will have in its motion. So another simpler example of that, or a second example of that, is maybe looking at a baseball pitcher throwing a baseball. So here's the baseball pitcher, and he has a baseball here, and he applies a force on the baseball, and the baseball goes out into space with a certain trajectory. And again, if you know some basic information about the person, the baseball, you can use these physical, classical, mechanical laws to predict exactly where in this trajectory the baseball will be at any moment of time. So that is really powerful for these laws to do. But here's the thing. These powerful laws that predict the trajectories of objects cannot be used for very small objects the size of an atom. So atoms are very small, as you know. So the typical atom is going to be from 0.1 to 0.3 nanometers in width. And so that is 1 angstrom to about 3 angstroms. So again, we cannot use classical physical laws to describe the motions of things in atoms. In particular, we cannot use these laws to describe the motions of electrons in atoms. So eventually what I'll do is I'll talk a little bit about a simple model of an atom that you can use to describe some properties of the atom. And so in this model, what we have is we have a nucleus, which I'm symbolizing by a positive sign here, and we have an electron, which we're symbolized by a negative sign. In this very simple model, it is thought that the electron travels around in an orbit around the nucleus. Now, this model can be used to predict some properties of atoms, but it's very incomplete. And we now know that electrons do not travel in defined trajectories around the nucleus. So this model really isn't correct. We'll talk about it, and we'll use the model to predict some properties, but overall, it is not a really good description to understand the motion of electrons around an atom. And so we use instead new laws, which are called quantum mechanics. And these are physical laws that you really need 4 semesters of calculus to understand. And they say some pretty amazing things about the motion of electrons around atoms. So if you have an atom here with its nucleus here, and so let's say you have an electron, I'll just draw it as a dot here. What the quantum laws predict is that electrons do not travel in trajectories in atoms. Instead, they have a completely random motion. So one moment you find the electron here, one moment it's there, maybe one moment it's here, one moment it's there, one moment it's there. Now you might say, oh, well, wait a minute. So wouldn't that mean that there'd be some kind of path that the electron takes to go from one place to another over time? And the answer is no. Electrons do not go in any kind of path as we might imagine it in the macroscopic world. Instead, they just appear in random positions. It's hard to envision this is because we have never seen anything at the level of an atom. So it's very hard for us to truly understand what the mathematical laws are saying of the motions of these electrons in the atom. Another weird thing that the rules of quantum mechanics tell you is that you can actually have electrons in more than one place at the same time. I'm laughing because it's almost embarrassing to say, but that is true. The laws of quantum mechanics predict that you could have electrons being at the same time at two completely different places. But there's another law you'll learn about, which is called the Heisenberg uncertainty principle, that says there's actually a range of places where the electron can be in the atom. But again, it can be within this range, but at two places at the same time. So we'll talk more about this later. So the first thing we're going to do is we're going to talk a little bit about light. And the reason why we're going to talk a bit about light is because light is used as a tool to understand how electrons move about in atoms and where they can be found in atoms and the energies that they have. And so maybe you've heard that light can be thought of as a wave. It is something called an electromagnetic wave. And so I'm going to be talking a little bit about how light can be thought of as a wave in the next presentation. Thank you for listening.